All right, so now we've learned about continuity. Let's talk about what types of functions that we already know about are continuous on their entire domain. Turns out most of the types of functions you've dealt with before are continuous everywhere they're defined. Polynomial functions, rational functions, radical, exponential, log, and all the trig functions. They're actually continuous on their entire domain. Now, that doesn't mean that some of them don't have discontinuities, like a rational function can have those vertical asymptotes, right? So they can have discontinuities, but those are also points where the function's not defined, therefore not in its domain. As long as one of these functions, a function of any one of these types, as long as it's defined, it's continuous. That is really going to be a huge help to us when we're trying to figure out limits later. So definitely remember that. So that begs the question, well, what types of functions have discontinuities? The first example we're going to look at is one of those rational functions. So let's look at the example x minus 1 over x squared minus x. So here's a rational function. It's a pretty simple one. We can do a little bit of simplification via algebraic factoring. In this case, our denominator there, we can factor an x out. That's nice and easy. And then we see a common factor of x minus 1. So I'm going to write equals 1 over x if I cancel the x minus 1 factor. But this is a caveat to this. These expressions are only equal as long as x is not equal to what? Well, 1. As long as it's not equal to 1. Right? Because 1 was the number that would give us a 0 in the denominator and make this function undefined. Right? So it's equal to 1 over x as long as it's not equal to 1. So that means the graph is going to look just like the graph of y equals 1 over x. We know what that looks like, of course, because we have studied our catalog of essential functions, and you've all memorized those. And you know you can draw their graphs quickly and from memory. Super useful. So it's going to look exactly like that, except when x equals 1, which is going to be about here somewhere, right at 1, 1. Right here, we'll have a little hole. So, what are the discontinuities in this function? Well, there's two. First, there's the hole, right? That type of discontinuity is called a removable discontinuity. So we have a removable discontinuity at x equals 1. We're just going to identify the discontinuities by the x coordinates they correspond to. So we have a removable at x equals 1. And we do have a second discontinuity on this function because this function has a vertical asymptote. It's undefined at 0, right? And it's approaching infinity. It's kind of shooting down to negative infinity if you come at 0 from the left. And it's shooting up to positive infinity if you come at 0 from the right. So we have an infinite discontinuity at x equals 0. There is one example of a function with discontinuity. Here's another one. For this, we're going to choose a function that involves an absolute value. This is a function I've shown you before, but I'm just going to bring it up again so that we can talk about it from the perspective of continuity and discontinuities. It's this function, the absolute value of x divided by x. This function, turns out, gives you either 1 or negative 1, depending on whether you're dealing with positive or negative numbers. It's definitely undefined at 0, because we can't divide it by 0. If you throw in a positive number, you just get x over x, which is 1. So this is going to equal 1 if x is greater than 0. If you throw in a negative number, you're going to get negative x in the numerator because you need to throw an extra negative to make it positive again, right? So you end up with negative x over x, which is negative 1 when x is negative. I explained that in a little more detail, I think, last time I brought up this function, so you can look back at that video if you don't remember. But here's the graph of this function. It's going to be at 1 on the right side and at negative 1 on the left side. So it's like a constant function, except that it has this jump at 0. So what are our discontinuities? We only have one. It's a jump discontinuity at 0. So in general, functions that are defined piecewise, like this function which we defined this way could also be defined piecewise as, like this, 1 or -1, depending on which part of the domain you're on. Piecewise defined functions can have jump discontinuities, so just be on the lookout for them. They don't necessarily have jump discontinuities because you could have, for example, the pieces of the function, the different pieces like line up with each other. So if they actually line up and meet at the same place and they have a point defined there, then it might not be discontinuous at all. Like, for example, I can grab a piece of paper. I can draw a piecewise defined function that might look like this. Right? It's got these like sharp corners here and here where the function definition changes from one algebraic expression to another, but maybe they meet up with each other, right? And then it's actually continuous. So not necessarily, but occasionally you can have these jumps.